Okay, so welcome everyone to the very last lecture of the course of your introduction to quantum optics. It has been a long ride, but I hope that you learned a lot and you enjoyed it. And for this last lecture, we will concentrate on the last part of the chapter that we were in, which was about the detection of the radiation coming out of an open system. And remember that so far we have, maybe let me write it here. So far what we have seen, apart from characterizing the output of the source, of the open source, we have also seen that if you just apply direct photo detection, so with a photo detector, we can use, we can just measure the output light directly. And then this, we saw that it's equivalent, or the photocurrent that appears in the photo detection is a stochastic signal that contains the moments of the photon number operator of the output. Okay, that gives you the photon number per unit time that is radiated, that are radiated from the system. Then, loosely speaking, with one photodetector measuring one specific field, then you have access to the photon number, okay, the photon number operator. Now it comes a question, and this is a part of what why we are doing this chapter today, that so is it possible by combining? So if we do a combination of several detectors, and maybe several sources with different properties, can we actually have access to other observables, not only the photon number, but maybe other observables? So then this is one of the questions that we will answer today. Okay, so today what we are going to see is the chapter about Homodyne detection, or the section about Homodyne detection. And as I will show you, so I will try to convince you that this kind of detection that I will explain in a second, but again, it's just a combination of detectors and sources. This Homodyne detection, it's equivalent to the measurement, if you want, of the moments, or again, the stochastic current generated in this detection will have moments from which you can infer the quadrature moments. Okay, so you can imagine that this is super important because in most of the course we have been characterizing actually quantum states by first and second order moments of the quadratures. So it's very, very important to have a way in the laboratory to measure quadratures, because those are the basic, absolutely basic observables from which we can infer what are the properties of any other observable of the system. So then Homodyne detection will allow us to do this. And so let me start by explaining what is Homodyne detection, and by this, you will see that very naturally we will get a definition of what is squeezing for the field that comes out of the cavity, that is not a single mode, but a complete field, okay? So let's see if I can draw the picture properly. So what we have done so far is the following. So we have essentially our source, okay? So from this source, that is an open system, we have some kind of field that is leaking out. and we were calling this the output field. So I will represent it with the vector potential. And then the last piece was that we were putting one photodetector somewhere, and then we were observing, or we were processing some kind of signal, the photocurrent, that is a stochastic signal that, as I said, has moments that are somehow proportional to the moments of the photon number of the output. So now what we are going to do is something a little bit different. We are going to add one more source. So we are going to do something like this. Now, apart from the source, that it's our main interest, okay? So we want to study properties of the output field. Apart from this one, now we have another source that we can call Coherent Source, whose properties we actually know very well. So these are like two mirrors of a coherent source that are coming out. And I will give you the properties of this source just in the next slide. But for now, just imagine that it's some kind of open system that is radiating a coherent light, okay? So like laser light. So it could be a laser itself. And we are going to call the output of this source, we will call it LO, okay? And LO stands for local oscillator. And I think you will understand the name soon, but just for now, it's just some kind of name. So the output of our coherent source that we know very well, it's very well characterized, and then we will use it as our reference, okay? That we call local oscillator. And we will represent it all the time with the label LO. So now what we do is something very simple. We just mix these two fields in a beam splitter. So we take here a beam splitter. And in this beam splitter, you essentially combine the output field with the local oscillator field, and then you produce another two fields that we will call just the plus field. You will see in a second why we call it plus, and then the minus field. And now the point is that now we have kind of two fields that we can measure, right? We have the plus field that we already have a photodetector there. And now we have another field, the minus field, and we can put another photodetector in this one. So now the question is that what we can do is process these two signals instead of only one. And we will call the corresponding photocurrents, we will call them J minus and J plus. And then we combine them in a subtractor, okay? So so we just take the signal plus, the signal minus, and we do the subtraction. And what I will show you is that the photocurrent that appears from here, so this is just the subtraction of the two signals. So this is J plus minus J minus, okay? This is, we will call it Homodyne photocurrent. And what I will show you is that this Homodyne photocurrent has moments, so stochastic moments, that will be proportional to normally ordered quantum moments of the quadratures of the output field, okay? So then let me go into the theory of this and let me show you how this is indeed the case. So I hope that the scheme is clear. So it's not very complicated. And this is one of the most common measurement schemes that people in quantum optics use in the lab, not only in quantum optics, but also actually in electric engineering as well, like in electronic circuits and so on. Okay. So then, in order to prove all these things, the first thing that I need is to characterize, or to tell you how we are going to characterize the coherent source, okay? So we need a model for the, let's say, the local oscillator. So in the model for the local oscillator, it's nothing special. It's something that you have already seen. What we will see, or what we will say, is that the output of the coherent source, that, as I said, we are calling it LO, local oscillator, at some position set in time t, is just equal to, okay, some polarization, some normalization factor, that for an output field, the normalization factor is this one. Some frequency, okay? So this omega LO, this will be the, what we call the local oscillator's frequency. For example, if our coherent source is just a driven cavity, then this would be the frequency of the driving, okay? And for a resonant driving, it will just be the frequency of the cavity. And then some output operator, and we will call ALO to this output operator, evaluated at some retarded time. So again, retardation will not play any role, but I just write it exactly how we have written for the previous examples. So this is the output field of coming out of the coherent source. And what characterizes this source as coherent, as we have seen from the previous examples, is the following, is that the if you want to evaluate any field correlation function of this output field, so imagine that I tell you what is the correlation function associated to n A-Dagger operators and m A operators, just like we have studied before. So if the source is coherent, this means that the output field is in an eigenstate of the output operators, a coherent state of the output operators. And then this means that this quantity here will just be a complex number associated to, or a multiplication of complex numbers associated to each of the annihilation and creation operators we have. So in particular, we will be able to write it in this way. So just some rotating factor, because you have some kind of coherent state rotating at the frequency omega LO. And then, so with a plus omega LT for the A-Dagger operators and a minus for the A operators, then some phase. So you have a phase for the amplitude of the coherent state, and you have M A operators and N A-Dagger operators. And then you have some amplitude. And then this amplitude, we will call it alpha of the local oscillator. And we have N plus M of them, okay? So what's important is that together with this oscillator frequency, then we have some phase that we can choose and some amplitude. So this is the phase and amplitude of the coherent output. Okay, so this is essentially the model that we can use for the output of a coherent source, for example, a laser or just a driven cavity, like we have seen that actually comes from driving with a laser and so on. So this is the model for the local oscillator. So that's a field that we know very well. Now, the other thing that we know is that the sources are independent. And I mean, this is obvious, no? Like we have our source and then we have our coherent source, our local oscillator source. And these two things are separate sources that have different Hilbert spaces and everything. So they are independent and their state is not correlated. And then this means that if I ask you what is the expectation value of any operator of any operator related to the output of our source with any operator related to the local oscillator, okay, this will factorize because the states are uncorrelated. So you will have something like this, and this is true for all times. Okay. Moreover, if I ask you what is a commutator between operators in the output and operators in the local oscillator, again, because they act on different Hilbert spaces, they will commute, okay? So this is nothing too deep, but something that you need to understand well. So then we have a source, and we can control in this source the phase and the amplitude, and also the frequency, okay? And it commutes, and it's completely independent from the output. Okay, so then now all I'm going to do is use these properties to show you that the moments of this photocurrent, okay, are proportional to moments of the quadratures of the output field, which is what I promised. So then for this, the first part, as you see from the picture, is I have to tell you what are these fields A minus and A plus that are measured by these two photodetectors. So of course, when two fields enter a beam splitter, they get mixed, okay? And in particular, with a proper adjustment of the phases and the materials of the beam splitter, because this expression I am going to show you is not completely general, so I will explain you. So the fields emerging from the beam splitter so as I say, with the proper combination of the electric coatings and combination of phases, like adjustment of phases, you can make it such that this is just the sum and difference of the output and the local oscillator fields. Okay. Oops, the fields depend on second. Okay, so you just have part of each beam is reflected, and part of each field is transmitted, and then you get these two possibilities. Either they add up or they get subtracted. So in principle, this is what we have, but so let's say that if the frequency of the local oscillator it's very close to the frequency of the source, which of course it will be the case, because if we are using a local oscillator that is of a completely different frequency than our source, we will not have any mixing between them. We will just have a combination of fields that will just be the sum without any interference of each of them. Then if we allow the frequency of the local oscillator to be close to the frequency of the source, then essentially within the slowly varying approximation for frequencies and so on that we have done before, essentially we can write these fields A plus and A minus in the familiar form, in which we just have a phase factor, an amplitude factor is omega LO, and then we have an operator that is actually an annihilation operator, satisfying canonical commutation relations in time. Yeah. And what's interesting is that we have that these annihilation operators plus and minus, they are nothing but the sum and difference of the output in the local oscillator annihilation operators. Okay, so now since we understand the properties of this operator, and these are the operators that we want to characterize, then in principle we have in these operators we have all the information we need. So in particular, now that you know this, then the photocurrent in these photodetectors, so in this one and this one, these photocurrents plus and minus, they will be related to the corresponding photon number operators. And which are these photon number operators? So these are just the A dagger plus minus A plus minus. And this, if you just expand it, you get 4 terms. And these 4 terms you can rewrite as the part that does not have interference. So this is the photon number of the output plus the photon number of the local oscillator. Okay. And then the part corresponding to the interference between these two. So let me call that H. Okay. And this H, I give it a name because it's actually the important operator in this business. It's just the cross terms or the interference terms. So you have the A dagger of the local oscillator with the A of the output plus the A of the local oscillator and the A dagger of the output. Okay? So this is the really relevant operator because, as I am going to show you right now, this operator encodes everything, all the information about quadrature operators and quadrature correlations. So in particular, it is completely trivial to show that if you evaluate the normal ordered product of operators H, let's say n of them, so the expectation value of this normally ordered product, then it's very simple to show that this is proportional to the amplitude of the local oscillator times the normal order of something that we will call x tilde phi of local oscillator out. So this is an operator. I will give you in a second the expression, but you can imagine that it's some kind of quadrature. Okay, and in particular, this operator it's indeed related to the quadratures, and in particular, it is the following. So we just have, so let's say that the quadratures that we want to measure are something like this, like e to the I phi local oscillator with the output field operators, okay, plus the Hermitian conjugate. So this is what we would call, so usually we put a minus in there. So this is the quadrature, this is the quadrature phi, okay, of our output field. However, what we get is not exactly this. It has one slight difference, and this difference is that in the phase factor, you get actually the oscillating frequency of the local oscillator. So these are not directly quadratures. I mean, they are quadratures, but they are rotating at the local oscillator frequency. So they are what we call slowly varying quadratures, because these operators, these output operators, they oscillate at optical frequencies, like we have seen from the previous examples. And then this frequency here, or this oscillation here, kind of removes that optical oscillation. So then what you end up with is an operator that evolves slowly compared to optical frequencies. And there are many lessons to learn from here. So the first lesson is that it's very difficult in experiments to measure instantaneous things at optical frequencies. So variations at optical frequencies. This is something that I have mentioned a few times, and now you can see it explicitly, because it's really, really complicated to resolve the fast optical scales. So then we are always going to talk about these slowly varying output quadratures. Okay, so instead of talking about the instantaneous one, so the one that it's kind of in the original Schrodinger picture or whatever. So then, on the other hand, now that we know that this operator H contains everything about quadratures, then the rest of the scheme, so in particular, the fact that we take the two photocurrents plus and minus and we subtract them to create another photocurrent, is designed only to remove everything from the plus minus operators that is not H, okay? So as you see, if I just do the subtraction of plus and minus, these n operators of the output and the local oscillator will go away, and then we will get only H, okay? So in particular, again, it's very easy to prove. That if I ask you what are the first and second order moments or correlation functions of this homodyne photocurrent, it's very easy to prove that you get that the first order moment is proportional to just the expectation value of the quadratures. And that the two-time correlation function is proportional to the normally ordered two-time correlation function of the output quadratures in normal order. Yeah. Okay, so this is very simple to prove. And for the proof of this, you only need one thing that that I still didn't give you, because you know how to relate the photocurrent of one detector with the number operator of the field that is arriving to that detector. But what happens if I ask you So you'll need so what happens if I ask you, how about the second order moment associated to the cross correlation between the photocurrents in two detectors? Okay. Then in this case, and of course you can extend this to any correlation function of several photocurrents or several photodetectors. It can be proven that this is proportional to the correlation between the in normal order between the corresponding photon number operators. So this is just a very natural generalization of what we already saw for one single detector. And it makes perfect sense because, of course, maybe naively, you would think that, oh, because these two detectors are independent, okay, because the detectors are independent, the photocurrents that they generate are independent. And that's not true, because if the fields that they are measuring are correlated, of course, the statistics of the photocurrent will be correlated, okay? That's kind of obvious. So in particular, imagine that you have a field in which whenever there is a photon in this arm, you know for sure that there is a photon in this arm, then you know that whenever you detect a photon in this photocurrent, you will also detect a photopulse in this one, okay? So you cannot claim that photocurrents of independent detectors are statistically independent. It's exactly the opposite, okay? They are correlated if the underlying quantum fields are correlated, okay? So then, so now that we understand that the homodyne photocurrent is related to moments of the quadrature operators, then so let's say that we are happy, and in particular, now I will always refer to fluctuations. So from now on, I will talk about how are the fluctuations associated to this photocurrent, which of course, as I am going to write in a second, it's related to the fluctuations in the quantum field. So this is the photocurrent minus the average of the photocurrent. And then this means that we will be interested in, let's say, second order moments or two-time correlators of this fluctuation of the photocurrent. And just based on the previous expression that I gave you, this is proportional to alpha of the local oscillator squared, and then exactly the same expression as before, but now with the fluctuations of the quantum quadrature instead of the quadrature itself. Okay, so here the fluctuations of the operator, as usual, are defined just as, oops, as the operator minus the quantum expectation value of that operator. Okay, nothing special. So then in principle, this is a very important result. So this is one of the key results of this chapter because it tells us that by measuring the moments of the homodyne photocurrent, then we have access to the normally ordered moments of the slowly varying quadratures of the output. And using the input-output relations, if the external field is in vacuum, we know that this ultimately will be proportional to the normally ordered correlator of quadratures inside the source. So this even allows us not only to characterize the output field, but also what is the state inside the cavity, inside the source, okay? So this will allow us, or this in principle is one way of measuring what is the steady state, or what is in general, the state of your open system, okay? So essentially, this is a very interesting result, but there is a problem, okay? So there is a but. So however, it's possible to show so in the same way that it's possible to prove this kind of expression, and I told you it's non-trivial, okay, but you can show this expression here. And in particular, note that I am always telling you that it's proportional to this. I never give you the proportionality factor, and I never give you the exact expression. So if I would give you the exact expression, you would see that it's quite amazing that if I ask you what is the fluctuations of the variance of this photocurrent associated to a photodetector, and this is completely general, it's just the photocurrent of any photodetector, okay? It's interesting that this goes to infinity, okay? For all time, for common photodetectors. So I don't know if you understand the physics of this, but this is very bad because this is telling you that essentially you have an average, that is the average photocurrent, and this photocurrent has a variance, and the variance at any time, it's infinity. So essentially, this is telling you, this result, that the instantaneous photocurrent is essentially hidden behind a massive noise wall, okay, or wall of noise. So as I said, I cannot prove this because it's a little bit tricky, but this is what happens in most detectors that are used in labs. So there are some modern detectors that allow for instantaneous tracking of the photocurrent, okay? But these are very expensive detectors and very, very state-of-the-art. And it's not the usual detectors that have been used in quantum optics traditionally, especially not at the beginning of quantum optics and in the 80s, 90s, and so on, okay? So then it's worth it that we see what do we do with this kind of situation. So we have a photocurrent that allows us to, gives us access to this kind of moments of quadratures, okay? And then allows us to characterize a quantum mechanical state perfectly. But unfortunately, in time, instantaneously, so if we want to know what is the value of the photocurrent in time or the average in time or whatever, this is not possible to find because it's hidden behind a massive wall of noise. So then what do we do? So is there a way around this or we just cannot measure? So of course you can imagine that I'm telling you this story because there is a very simple way around it. So if we have a lot of noise, but it's noise that is completely flat in the time domain, so it's the same noise for all times, then we know that if we do the Fourier transform of the signal, okay, then all the noise that was completely extended in time, it will get completely localized in frequency, okay? Which means that only one frequency will have noise and all the other frequencies will be free of noise. So then for this reason, in experiments, we usually don't work directly with photocurrents, but we usually work with something that you might have heard or even used if you have been in the lab doing some experiments. And I don't mean quantum optics experiments, I really mean any type of physics experiment that has photocurrents and so on. So we usually consider what is called the power spectrum. And the power spectrum, with full generality, is not exactly a Fourier transform, but you will see that it converges to a Fourier transform in a second. It's the following. So imagine that you are measuring during a time td, okay? So I will call td to the measurement time. And then what we do is just an integration over times of a cosine signal at some frequency omega that we can choose with the two-time correlation that we are interested about. Okay, so let me say it again. So TD is just the measurement time. So for how long we are integrating or for how long we are looking at the photocurrent. Omega is what we will call the detection frequency or noise frequency. So we usually call it detection frequency or noise frequency. And this is one of the nice things of having converted, let's say, quantum fluctuations into just stochastic fluctuations of a signal, that we can take the signal, that is an electronic signal, and now we can post-process it in any way we want. In particular, we can multiply it by a cosine function, and then we can add all for all times. This is something that is very simple to do. And in particular, it's already integrated in most photodetectors. You have already the power spectrum analyzer within it. So then, as I was saying, because this thing here is similar to a Fourier transform, and I will show you that it is exactly a Fourier transform in the proper limit. Now the noise wall will get confined on the range of omega between 0 to 1 divided, so something proportional to 1 divided the time of observation, okay? So then if you are measuring, if you are integrating over a sufficiently long time, then only the frequency, the omega frequency equals 0, will have noise. All the other frequencies will not have a variance that goes to infinity or anything like that, okay? We'll give you a signal that is not infinity that you can measure. And as I was telling you, so if we have stationary sources, and what characterizes a stationary source is that this kind of two-time correlation functions, as we have, I don't know if we have seen an example, but certainly we will see, yeah, we saw some examples with the G2 function, but as we will see now, this two-time correlation function, whenever your source is stationary, it usually depends only on the time difference, okay, in the absolute value of the time difference. And then it's very easy, once you have this property that this function in the kernel of the integral depends only on the absolute value of the time difference, then it's very easy with variable changes to show that when the integration time goes to infinity, then this power spectrum gets a more familiar expression, which is just the Fourier transform. Okay? So then now you understand that essentially what we are interested about at the end of the day, it's simply the Fourier transform of the two-time correlation function of the photocurrent. That's what's relevant for our purposes. And yeah, I think I will make a break now and then we continue. But I hope that this is relatively clear, and then you will understand why we will work with one special object that is called the squeezing spectrum, and that's what will characterize the quadrature fluctuations outside an open source. Okay. Okay. So let's meet in 10 minutes, so at 1:55. Okay, so welcome back. So what I was telling you now is that what is usually measured in experiments related to second order moments in order to characterize the output fields is the power spectrum. And the power spectrum, essentially, it's the two-time correlation function of the Homodyne photocurrent that you just Fourier transform, okay? So then, if we are interested on the Fourier transform of the second order two-time correlation function of the photocurrent, this means that at the end of the day, at the quantum mechanical level, what we are interested about, it's something that we will define as the quadrature noise spectrum. Okay, which is nothing but the following. So we will call it V of phi, for phi is the quadrature of omega, which is the frequency of the Fourier transform. And this is just a Fourier transform, or more generally, a power spectrum, but let's focus on stationary cases. And then we get this Fourier kernel, and now we have here the two-time correlation function of the quadrature fluctuations. Okay, so everything I have introduced is just kind of motivation for introducing this specific object that is the most important object when we want to characterize how is noise in phase space for the field coming out of an open system. Okay. Then now what's interesting is that this expression here, well, we can do several things with it. So the first thing perhaps is just, let me just write it down, that of course the two-time correlation function of this output operators of T and T prime, so quadratures. And we can write it in terms of the normal order form, okay? So just bringing annihilation operators to the right and creation operators to the left, using the commutation relations of the output field, we can just write it in this way. So the commutator gives us this delta function contribution, and then we have the same expression, but in normal order. Okay, here I didn't do anything. I just rewrote what's inside of this expectation value. I rewrote it as the normal order expression plus whatever you need to add for with the commutator. Okay. Then if we take this expression here and we just insert it in the integration. So let me make it small and bring it here. So essentially what you are going to get is something of the following type. So this is one thing. And then the other thing is I will assume a zero temperature. So we assume that the external field is at zero temperature, which is a common thing as I have mentioned a few times in optical experiments. So it's room temperature, but at room temperature, the number of optical excitations, it's essentially zero, or excitations at optical frequencies is essentially zero. Then this means that once we have something in normal order inside the expectation value, then we can relate it to the intracavity operators or the system operators instead of the output operators with a factor square root of kappa. So then in particular, at the end of the day, we get an expression that looks like this: 1 plus kappa, and then the integration of the two-time correlation function, but now not of the output field, but the system field or the system observables. And in particular, this system observables or this system quadrature, x phi, it's nothing but exactly the same slowly varying envelope as we had. But now we have here the system operator instead of the output operator. Okay, so let me maybe remind you very quickly, because I'm not sure how much you remember of it, but I hope a lot because you will have the exam next week. But the output operator, remember that it can be written as 2 times kappa, the system operator, minus the input operator. Okay. So in particular, for an optical cavity, this kappa is equal to 2 times the loss, so 2 gamma, and S is nothing but the annihilation operator, while for an atom, this is just the decay rate, and this is the ladder Pauli operator. Okay? So again, I will keep this, but I will make it small and just put it here as a reminder. Okay, so then this is essentially the final object that we are going to be interested in. It's just called quadrature noise spectrum, okay? And it's 1, so it has a baseline of 1 plus something, and all this something, so all this quantity here, we usually call it with a name because it's just the part that we need to calculate. Oh, sorry, I said something stupid. This is in normal order. I hope that you understood. Okay, so we write this as delta function plus normal order, and then the normal order, we can write it in terms of intracavity or system operators, okay? So then this normal order part of the spectrum, we call it squeezing spectrum. And you will understand in a second why we call it squeezing spectrum, because whether you have squeezing or not in your system, it's completely determined by this part in here. Okay? So, and as I said, this object here, it's also a slowly varying quantity, so a slowly varying system quadrature. Okay? And then finally, so before I proceed to explain you what are the physics of this object or what is the interesting physics of this object related to squeezing, let me just make one note. And the note is that it's possible to show that similarly to the uncertainty principle, or the uncertainty relations, this noise spectrum also satisfies some kind of uncertainty relations, which are these ones in here. So if you consider the product at the same frequencies of the quadrature noise spectrum of two orthogonal quadratures, okay, so the position and the momentum, for example, this has to be larger or equal than 1 for any field, doesn't matter which one, okay? So this is a physical property, just like the uncertainty principle for a single mode or for a mode of a cavity, okay? So then now we have the object that we are interested about, and we have some uncertainty relation for it, and we know how to evaluate it from correlation functions of the system, which is what we know how to calculate with the results of the previous chapter, okay? So now the question that I want to, So the question that I want to address before I go to one specific example is that given that this is the observable that we usually experiment with in the lab, based on it, let me give you a practical definition of squeezing. Okay, in the output of a given source. Okay. So let's talk about squeezing. So I remind you that this was at the very beginning of the course, that we defined squeezing motivated by high precision measurements or high precision encoding of information. So what I told you is something like this, that usually the way that we sense or do sensing or encode information is by having a signal that we want to either measure or transmit. And we encode this signal as modulations in the quadrature, okay, of our electromagnetic field, okay? So essentially this means that in phase space, if you have a single mode, then we were saying that the point in phase space where this mode is not fixed, but it starts moving, oscillating at the frequency of the signal, or moving according to the pattern dictated by whatever signal we want to measure, okay? Then we define the squeezing based on the following fact, that if we have a coherent state or just a vacuum state, then we have an uncertainty, so we have some fluctuations, some vacuum fluctuations. And these fluctuations, these 0-point fluctuations, if the signal is very weak, if the signal that we want to measure or to transmit is very weak, then if these fluctuations are much larger than the motion induced by the signal, then we cannot resolve it, okay? We cannot measure it because it's within the noise. So then we introduce the squeezed states as the states in which the noise is reduced, okay, in one direction of phase space, such that if we encode the signal in that direction, okay, then at the end of the day, we will be able to resolve even if it is just a tiny oscillation, okay? Now we have a completely different view of what we are measuring. We are not measuring what is the state in phase space. We are measuring this output spectrum or this quadrature noise spectrum. So in particular, because this is a spectrum, okay, any signal that is encoded as quadrature fluctuation So any signal encoded as quadrature fluctuations will show up in the spectrum as a peak. Okay, so just imagine that if what you have is a signal that is oscillating periodically, so it's modulating the quadratures periodically, this periodic modulation at a given frequency will show up when you do the Fourier transform as some kind of peak, okay? This is exactly what happens in LIGO, for example, for measuring gravitational waves. So it's good to keep this example in mind. So imagine in LIGO, what happens is that you have your interferometer, which is essentially a cavity, okay, some kind of cavity. And then the gravitational wave is essentially changing periodically the length of the cavity, okay, such that this periodic change in the length of the cavity changes periodically the frequency, which changes periodically at the end kind of the quadrature properties, okay? Then what you are measuring when the light comes out of LIGO, of the interferometer, is precisely the power spectrum associated to the quadratures. And essentially, the gravitational wave should appear as one peak in this spectrum, okay? Now, the problem is, if we have a vacuum state, okay? So imagine that in our LIGO experiment, we are using only coherent light, so only lasers inside the interferometer. So if we are using vacuum or coherent light, like in LIGO, so laser light, then if you just look at this expression, everything that is in normal order doesn't contribute when the state is coherent or vacuum, okay? So then the quadrature noise spectrum is equal to 1 for absolutely all frequencies, okay? So for vacuum or coherent light, you know that this quadrature noise spectrum is equal to 1 for all omega and phi, okay? Then what happens is the following, that when people at LIGO check how is the spectrum, how is V of a given quadrature, okay? As a function of omega, what they observe is essentially something like this. So at 1, they have something flat. Then at some point, they have a peak in the spectrum that is a gravitational wave, or maybe a series of peaks if the gravitational wave is not perfectly a harmonic wave, okay, a plane wave. It's something more complicated, but just imagine that we have a single peak. And then this is what happens. If there is no signal, there is no peak, and all the spectrum is at 1, okay? And that basic signal in the spectrum, we call it shot noise, okay? Now, on top of this shot noise, you have the signal that you want to measure, okay? But you see that essentially the signal to noise ratio, okay? So how much noise do you have in the spectrum compared to how is the peak, okay? How is the peak above this noise? It's fixed, let's say, for a coherent state. That's equal, the shot noise is equal to 1. So then the signal to noise ratio is exactly 1 over, or it's proportional to the signal, okay? So if you want to measure signals that are very tiny, you will not be able to do it if the signal is below 1 in this normalized form of the spectrum, okay? Then it makes sense in this kind of setting, in this kind of scenario, to define the squeezing in the output field as, or to say that your output field is in a squeezed state whenever, for some quadrature phi, then the spectrum at some frequencies, it's smaller than 1. Okay? So if the spectrum is smaller than 1 for some phi and omega, then this means that essentially now your signal to noise ratio will improve. And this is easy to see just from the plot. So again, we have the same plot. But now imagine, for example, well, here we have the 1. So now imagine, for example, that this, as we are going to see with one example, this spectrum looks somehow like this. So it starts being 0 at 0, and then it goes up to 1. Okay? So now what happens is that the signal, imagine that the signal is around here. So in the absence of signal, the spectrum just looks like this. So it starts at 0, but then it goes towards 1 for large frequencies. But then in the presence of the signal, now the signal is present in here. But now you see that the noise, I cannot even show it. So the noise below the signal, it's actually very small, which means that if you are able to create this kind of states that have this power spectrum, then the signal to noise ratio improves. Okay. So this is just one example, but whenever you have some frequencies around which the quadrature noise spectrum is below 1, then you know that any signal that appears as a peak around that area will have a signal to noise ratio that is better than what you can get with just coherent light, okay? And this is precisely what is used now in the second generation or the third generation, I don't know, the latest generation of LIGO, of the LIGO interferometer. They are using squeezed output light, in particular from a source that we are going to study now, that is called optical parametric oscillator. And they are injecting this kind of squeezed light into the interferometer instead of just coherent light to improve the signal to noise ratio at some specific frequencies in the spectrum where quantum noise, so this shot noise in here, it's very relevant. It's the relevant noise that limits the sensitivity of the experiment. Okay. So I hope that this definition of squeezing is kind of intuitive once you know that this is the quantity that you are interested about for output light. I remind you, you are interested about this quantity because you are interested about the power spectrum of a two-time correlation function, because instantaneous signals are essentially impossible to measure, okay, except for very, very complicated and special and expensive types of photodetectors, okay? So I know this is a bit technical, but I just want, especially for you to understand that all these physics of single mode states, that of one harmonic oscillator, are very nice when we are talking about fields inside a cavity or a single atom and things like that. But whenever we start radiating into free space, and whenever we start measuring the light that is in free space and so on, then we have to really change the view that we have on all kind of single mode states, but we can still keep the same kind of philosophy, the same kind of spirit, in particular when it comes for to the definition of squeezing, for example, okay? So then, if this is clear and there are no questions, if there are, please just stop me. But otherwise, I will move on to the final part of the lectures, the final part of the course, which will be one specific source that is called optical parametric oscillator, okay? And you will see that with it, you can generate a squeezed light in the sense that I have defined in here, okay? So then let me start. So let me start by telling you what is an optical parametric oscillator. So an optical parametric oscillator is something that you have almost already seen in the course. So it's just an optical cavity that it's open, okay? And where we introduce a second order, so a material, a dielectric material with second order, second order response to the applied field. So second order optical nonlinearity, okay? This is something that you have already seen in the context of a closed cavity, okay? And I remind you that it led to a Hamiltonian. So this means that the Hamiltonian inside the cavity, the full Hamiltonian, is essentially the free Hamiltonian of the cavity mode that you are that you are kind of generating down conversion on, or you are generating with the second order nonlinear material, and then a Hamiltonian that we wrote as something like this in the corresponding chapter of light matter interaction. Okay, which I remind you that this we call down conversion. Maybe I need a bit more space. Within the parametric approximation for the pump. So I remind you just very quickly that what I am describing here is something that we call down conversion, which means that when we shine light of frequency omega 2 onto a material which has second order nonlinearity, we can generate a field at half the frequency, or around half the frequency, that we call omega 0, okay, through this kind of Hamiltonian. And this is what we call spontaneous parametric down conversion. And of course, I remind you that this frequency omega 2 is approximately equal to 2 times the frequency omega 0. This is for energy conservation, okay? And omega 2 is the frequency of the pump. And this Hamiltonian is just the Hamiltonian of down conversion when you make the approximation that the pump field is just a strong coherent laser that is fixed. It doesn't have dynamics, you are not changing, and it gives you just some effective coupling G, okay? Or we call it dressed down conversion rate. So this is just kind of a reminder of what parametric down conversion was, or how it was described with a Hamiltonian. And now that we have down conversion in an open cavity, then we know that the open cavity, or the field inside the open cavity, in particular the field at the down converted frequency inside the cavity, which we assume it's a resonance of the cavity, can be described through a quantum Langevin equation that looks like this. Just the time derivative of the annihilation operator in the cavity, it's equal to some damping, some free motion. Now the intracavity Hamiltonian of down conversion that gives a Heisenberg type of contribution that looks like this. Dagger. And then finally, the input operator. Okay? And I remind you that if we are working at 0 temperature, then this input operator has 0 average, 0 expectation value, and it has the 2-time correlation functions in normal order. So either this one or this one with the A dagger are also equal to 0. Okay? And well, this comes out from the commutation relation, but let me write it once so I'm sure that you remember. If I ask you a 2-time correlation function in anti-normal order, so AA dagger, this is the delta function of t minus t prime, of course. Okay? So this is the model for an open cavity where we put inside a crystal with second order nonlinearity. At least a model only for the down converted field. So with the pump just approximated as a classical source that is just giving you some amplification. And in any case, this is just some quantum Langevin equation that can be satisfied by some kind of open system, okay? And what it is not super relevant for what I am going to explain. It's just interesting, just so you know that it can be implemented in the laboratory. And as I said, this kind of source is the kind of source that we use in the LIGO experiments in order to generate squeezed light that we use for the interferometer to improve the signal to noise ratio, okay? But the important point for us is that now that we have a model for the source, for what's happening inside the source that we want to characterize, we can evaluate the quadrature noise spectrum, because we only need to evaluate the normally ordered 2-time correlation function of the slowly varying quadratures of the system, okay? And then this is what we will do in the remaining of the class. It's not very complicated, but it just has a couple of funny things. So the first thing I want to do is that you see that this equation depends on time explicitly. So we are going to do a variable change or move to a rotating picture in order to discount this time dependence, this rotation. So in particular, let me define some slowly varying annihilation operator inside the cavity, which will be just the annihilation operator that we multiply by a rotating phase at frequency omega 2 half, okay? So this is a slowly varying annihilation operator. Okay, then just with this definition, we can rewrite the equation in a way that it's not time dependent anymore. And in particular, it looks like this, gamma plus I delta, a tilde, well, I don't need this T. Then plus G, a dagger, and then plus square root of 2 gamma, and then some input operator that it's also an input operator that is slowly varying, or is multiplied by this phase factor. But what's interesting is that since the input operator is delta correlated, okay, then this slowly varying input operator satisfies exactly the same correlation or statistical properties as the original one. So in particular, these ones in here. Okay, and the same if we put the dagger in here. So essentially we get the same, exactly the same equation as we had, but without time. And also for the same price, note that if we choose the frequency of the local oscillator to be exactly half, so omega, the pump frequency divided by 2, then what we defined in the previous section as the slowly varying quadrature, but it was what we discounted was the frequency of the laser or the local oscillator, not the frequency of the pump, okay, like here. But if they coincide, and that's what you have to do in an experiment, then this slowly varying quadrature becomes exactly the quadrature associated to the slowly varying field, the slowly varying intracavity field. Okay? So, and in particular, this is the Homodyne. So it's the Homodyne measured quadrature. Okay, so directly from this equation, we obtain a solution for this A tilde, and this A tilde directly gives us the quadrature, the slowly varying quadrature that we are measuring in Homodyne detection. So then it's pretty simple to evaluate the power spectrum that depends exactly on that, on X tilde. So that's what we are going to do. By the way, I hope you remember, but this detuning that we are going to set to 0 anyways in a second. But just as a reminder, this is the frequency of the down-converted mode minus half of the pump frequency. Okay. So if you want it in resonance, then the pump has to be exactly equal to 2 times the frequency of the cavity at the down-converted frequency. Okay. So then, so this is essentially the setting that we need to solve in order to calculate the output spectrum. And in particular, let me do it for the tuning equals 0 because it becomes very, very easy. And also, let me define the position and momentum quadratures. I mean, or remind you that the position quadrature is just the quadrature for phi equals 0. And the momentum quadrature is just the general quadrature for phi equal pi over 2. Okay. And then using these two quadratures, the equation before, so the quantum Langevin equation, in terms of the quadratures, looks in this very simple way. It just looks as two independent equations for each quadrature that look like this. This is a 1 for x, and this is a 1 for p. And the nice thing is that these input quadrature operators, which of course you can imagine that it's nothing but just for any phase phi, is just a quadrature associated to the input operators. So let me write it down like this. It satisfies the following statistic properties. So of course the average is 0, just like for the input operators. But also the 2-time correlation function of actually any two quadratures. So it doesn't matter, any two quadrature angles. This will be equal to a phase factor and then a delta function. Okay, so this is something that you can show very easily. So starting from the quantum Langevin equation for the annihilation operators, then using the definition of the quadratures, you can see that for the position and momentum quadratures, the quantum Langevin equations are transformed into this. Okay. If you want, these are just the real and imaginary parts of this equation in here. Okay. So then now the solution of this equation is immediate because now we have two linear differential equations that are decoupled. Okay. And this gives us solutions that we can write in the following way. So I remind you that we have already worked a lot with this kind of linear equations forced by some time-dependent term, and they always look like this. So first you have an initial condition, and then the exponential of the linear coupling rate. Okay, plus, and now we get the integration in time of the same kind of exponential, but now of t and t prime, so t minus t prime, so the time difference and the history of the time-dependent force, okay? And the same for P. Okay? So then, now that we know the properties of the input operators, because they are here, then it's very easy to find what are the two-time correlation functions or whatever we want to understand from these two quadratures, okay? But there is a very interesting point that we need to discuss, which is the following, and then we can make a break, that when gamma is larger than G, okay, then this, so let me put it in another way. So for the P quadrature, this object in here, gamma plus J, it's always positive, and then this is always an exponential that decays with time, okay? So then in here, for long times, the part that depends on the initial condition is washed away, and the part that depends on the input operator will finally give you some kind of a stationary state. Now, in here, it's a bit different because you see that here we have gamma minus J. This means that whenever J is smaller than gamma, then indeed, the initial condition is washed out for a long time, so asymptotically. So remember, asymptotically means when time goes to infinity. However, if gamma is smaller than J, so think what this means physically. If the down conversion rate is faster or it's stronger than the losses in the cavity, then a lot of photons will start accumulating inside the cavity before they can go out of the cavity. And in particular, this tells you that the number of photons will increase exponentially. And this is shown because X tilde increases exponentially. Okay, and in particular, if it increases exponentially, then it's failing. Let me write it properly. Failing to equilibrate. So it doesn't reach an asymptotic equilibrium state. So, of course, this is not a real physical effect. This is an artificial effect that we have created because of the parametric approximation. And I explained it to you in a second, but essentially what this means is that the parametric approximation fails. And this makes perfect sense because the parametric approximation was that we assume that the pump is a fixed energy source, okay, that doesn't change. But if now we are using that source to make an exponential increase in the number of photons inside the cavity, this means that we are really starting to see the regime in which we are removing a lot of energy from the source, okay? When the increase wasn't exponential or was kept small, that was fine, because if we have a very large energy source and we create only a few photons, then that's not a problem. The energy remains more or less the same. But if now the number of photons grows too far, okay, then you cannot assume that your energy source is not changing. You need to introduce dynamics in your pump, okay? So whenever G is larger than gamma, this model that we have, it's not true. okay? You need to include the dynamics of the pump field. And that's something very interesting, very interesting that in a more advanced course you can see, and it's not difficult to do actually, but it requires a bit more complicated master equations. But it's still relatively simple to do and to analyze with approximate techniques. But in this course, of course, we are just going to remain in this region, gamma larger than G. So the down conversion rate is not fast enough to accumulate many photons inside the cavity. They will leak out before they can grow exponentially. And essentially, this is actually the regime in which most experiments are done in order to generate squeezed light, okay? So it's the most relevant regime anyways. So let me then maybe finish just by telling you one thing. So as I said, we are interested in calculating the quadrature noise spectrum, but it's also interesting, since we have it already, to find what is the state inside the cavity, okay? So this is the state of our open system asymptotically in this regime. So let's do it. This is something that we were doing in the last chapter for an empty cavity. And this is your first example of a cavity that contains something that is non-trivial. So this regime is called below threshold. And the point at which the number of photons starts increasing exponentially, we usually call threshold. That's why this is below threshold, okay? So then it's very easy to show that the asymptotic state in this rotating picture that we are, okay? So it has the following properties. First of all, if I ask you what is the mean vector of your state, well, first of all, because the quantum Langevin equation is linear, okay? It's still linear, even though it has a dagger in here, but everything is linear in A and A dagger. Then your state will be Gaussian, okay? The state inside the cavity remains Gaussian. Then, if I ask you what is the mean value of this Gaussian state, if you just look at this expression, you see that for time going to infinity, the initial condition doesn't matter. And then the input part is equal to 0 because the expectation value of the input operator is equal to 0, okay? So this is 0, 0. Now, if I ask you for the covariance matrix, so for this, you need to evaluate the first and second order moments of the A and A dagger operators, and then do exactly what we did in the previous chapter for the examples that we consider. But it's just very simple to show that this is equal, this covariance matrix is equal to this one in here. Where this sigma parameter is just G divided by gamma. So it's a normalized down conversion rate. So then you see that this is a very simple state. This is a state in which essentially it's centered in the origin of phase space, and then it has fluctuations that are in the directions. So the normal directions are x and p, so the positional momentum. And in particular, you see that when there is no down conversion, so when G is equal to 0, so sigma is equal to 0, this is just the covariance matrix of vacuum, which it's already what we knew. Like if you are not doing anything on the system, it remains in the vacuum state, or after it throws away all the photons because it's an optical cavity, then it goes to the vacuum state. However, now what's interesting is that if we plot the variance of the position and the variance of the momentum, what we get as a function of the down conversion rate, what we get is something like this. So let me write here. Let me see if I do it properly. So this is the 0.5 line. This is the 1 line. And let's say that we can do things only right before sigma equal 1. So when the down conversion rate is equal to the decay rate. So this is sigma, and then we have the following. So if you calculate what is the, so this goes up to infinity, what is the variance of the position quadrature? It goes like this. So it starts at 1, and then as you increase the down conversion rate, the steady state becomes with more and more fluctuations in the x quadrature. However, what's also interesting is that the one for the momentum looks like this. I think I did it too much. Something like this. So this is the variance of the momentum quadrature. And you see that it goes down to a 50% squeezed state. Okay. But what's interesting is that while the momentum quadrature has 50% of squeezing inside the cavity, the position quadrature has infinite fluctuations. Then this means that the state inside the cavity is not a minimum uncertainty state. Okay? Because the product of infinity with 0.5 is infinity, is not equal to 1, which is the minimum allowed by the uncertainty product. Okay? So then you have found that if you put a down conversion crystal or the electric with second order nonlinear, so optical nonlinearity inside a cavity, and you let it radiate, so it's an open cavity, then asymptotically, the state will be a squeezed state, but not a minimum uncertainty state, okay? And the maximum squeezing that you can get is 50%. And it's exactly at the condition that the down conversion rate matches the cavity decay rate, okay? So this is just for the steady state inside the cavity. And now after the break, what we will do is analyze what are the squeezing properties outside of the cavity, okay? And as you can imagine, if there is a squeezing inside the cavity, you can expect that there will be squeezing outside the cavity, but we will get a couple of surprises. So let's regroup again at 3, or yeah, maybe we can do 3, 2, okay? 302, and see you just in a little bit. Okay, so welcome everyone. Welcome back. So just one remark that I forgot to make. Of course, I'm doing this calculation in the Heisenberg picture with the quantum Langevin equation, but you could do it as well with the master equation and a quantum regression theorem, just like we calculated all the G2 functions and so on, or the correlation functions for the previous examples, okay? The reason why I do it in the Heisenberg picture is not because it's more like easier or anything, is just to show you an example of how to do it in the Heisenberg picture, because everything that we did in the previous sections was in the Schrodinger picture, okay? So, okay, but in any case, you see that using the quantum Langevin equations, we already have found what is the state of the system inside the cavity. It's a Gaussian state that it's in a squeezed state for any value of the down conversion rate, but it's not in a minimum uncertainty state, okay? It has momentum squeezing, but it has a position anti-squeezing that is much larger than the squeezing of the momentum. Okay, so now our goal in these final minutes is to calculate this function in here, okay? Or if you want, this function in here. So the two-time correlation function of the output quadratures. And this we will do very easily from these equations in here, or from these solutions in here, okay? So in particular, all we need to do is write the output. So essentially now I'm going to evaluate whether the output has any squeezing in the definition that I did before. And for this, all we need to do is, first of all, we write the output quadrature as a function of 2 gamma, and then the intracavity quadrature plus, minus the input quadrature. Okay, this is just the input-output relations, but for the quadratures instead of for the annihilation operators. Then I will use a combined notation both for the position and momentum quadratures. So in particular, we have seen already that when t goes to infinity, the solution for the intracavity quadratures at time t infinity, it's equal to square root of 2 gamma, and then, well, the initial condition is washed out already. And then when time goes to infinity, we have left only the integration of the input operator that we can write like this. Okay, so I just remind you very quickly. So look at the expressions. So the position, it's equal, this goes away. So the initial condition goes away. And then we are left with 2 gamma, square root of 2 gamma, and the integration of an exponential with some rate, okay, that I will call lambda, times t minus t prime, and then the input operator at t prime. But I just make now the variable change that t minus t prime, I call it tau, okay? And then I get the usual form that we were working with in the previous chapter, which was this one in here, okay? In which you integrate over the history, t minus tau prime. And now the same expression you get for the momentum quadrature, but now with a different lambda, okay? Instead of gamma minus g is gamma plus j. And in particular, so let me tell you here. So here the phi will be either 0 or pi over 2. And then the rate lambda 0 is, this should be gamma minus j. And the rate for the momentum quadrature is gamma plus j. Let me see, because I have it the other way around in here, but that's not true. Yeah, it's gamma minus j. Okay. Okay. So then this thing combines both expressions. Then, if we want to evaluate the correlation function of the output quadratures for momentum or position, so the first thing we need, as I said, is this two-time correlation function that we will do the Fourier transform of. And of course, I am writing it, or we are interested in the t going to infinity limit, but I will not write it down explicitly just because it's annoying to do it all the time. And then now using this expression for the output in terms of the intracavity and the input one, we will get 4 terms in here. First, the terms that involve 2 intracavity ones. Then the term that involves 2 input ones. And then we get the cross terms. And the cross terms, they look just like this. Okay? Then now, knowing what are the correlation properties or the statistical properties of the input operators, okay, which we have in here, it's just very easy. And what is the dependence of the intracavity ones in terms of the input ones that we have in here? Then you can evaluate all these 4 correlators. And in particular, it's completely trivial. Well, this one is just by definition. You get delta tau. This one in here, which is the cross correlator, you can prove on your own very easily that this is 2 gamma and the exponential of minus lambda phi absolute value of tau. And then this one in here, it's one that, since we still have time, I want to show you how to evaluate it. Okay, just because I want to show you something about how to do integrations with the delta function that I don't know if you are familiar with. So then I think it's useful to do it. In any case, it's just one blackboard, it's not a big calculation. So then let me do this calculation in here. So we are interested in the limit when t goes to infinity of x phi of t with x phi of t plus tau. And this, just using the solution of x as a function of x in, so the intracavity as a function of the input, we get this. So one integration goes until t, the other one goes up to t plus tau, and then we have here the exponential kernels of tau 1 and tau 2, and then we have the correlation function of the input. And this is t minus tau 1. And this is the upper limit, which is t plus tau minus tau 2. Okay? But now we know that this thing in here is just the delta function of tau 1 plus tau minus tau 2. Okay? So then, of course, in principle, you would tell me, oh, this is trivial, right? Because I have a double integration in tau 1 and tau 2, but I have a delta function of tau 1, tau 2 that tells me that tau 1 or tau 2 is equal to tau 1 plus tau. And then I can remove one integration and just do the integration in tau 1, setting tau 2 equal to tau 1 plus tau. That's kind of true, but we have a small problem. That is the small issue of the integration limits, okay? So we have an integration limit that goes all the way up to t and another one that goes to t plus tau. So which integration limit should we use? So this actually depends. So you have to be careful. You have to really analyze carefully so for which values there is overlap between the tau2 and tau1 plus tau, okay? So in particular, let me just show you very easily, very quickly, that what happens is the following. So imagine that tau is larger than 0, because it's different for tau larger or smaller than 0. So if tau is larger than 0, then let me put it this way. So we have in here the integration domain, so tau1, tau2. And now the integration domain is the following. So in tau1, we go all the way up to t. And in tau2, as you see in the integration domain, we go all the way not to t, but to t plus tau. So, and then t is somewhere around here, for example. Okay, tau is positive, so t plus tau is above t. So now what happens is the following. So this is the integration domain. And then this is the line tau1 equal tau2. And this line in here, so this is tau. Is the line tau2 equal tau1 plus tau, okay? Then you see that when, so am I doing it correctly? Error. Yes. Then you see that when tau1 is equal to 0, then tau2 is equal to tau, okay? And this is precisely the line, okay, that the delta function tells us that we need to choose. But of course, we need to choose it only up to the integration domain. So the integration domain reaches this point in here, and that's as far as you can go. So you cannot go outside of the integration domain in your remaining integral. So this means that the remaining integral can be written as, so you have removed tau, so you have removed tau2 because we can remove it from the integral and just set tau2 equal to tau1 plus tau. And we are left with an integral in tau1, but then the integration in tau1 goes from where to where. So we just look. So it's this whole line, but this whole line starts at tau1 equals 0 and ends at tau1 equal t. So then the integration domain is 0 to t, okay? Or you could do it in tau2 if you prefer. So this is why I want to show it. So now instead of setting tau2 equal tau1 plus tau, you could set tau1 equal tau2 minus tau, okay? And then do an integration in tau2. But then now, if you look at the integration domain along this line, you see that the integration goes from tau, so in tau2, which is this axis, goes from tau to t plus tau. So we get this. So either you do integration in tau1 or in tau2, and the integration limits are different, okay? All of them span over a time t, but from different origins, and that's it. So then this is essentially for tau larger than 0, then for tau smaller than 0. So by the way, another way of saying this, which is easier, but I just wanted to do it carefully because in some situations it might not be as easy as this one. Another way of saying it is just that you are just asking, where do these two functions overlap, or these two integration domains overlap, okay? And then you stick to that domain. So in particular, you see that tau1 goes from 0 to t, and tau2 goes from 0 to t plus tau. So the overlap is only 0 to t, okay? So that's all you can do. Now, what happens for tau smaller than 0? Let's apply the same logic. The same logic means that now tau2 goes from 0 to t minus the absolute value of tau, because tau is negative, okay? So then the integration domain of tau2 is smaller than 0 to t. So then finally we should get an integration in tau that is from 0 to t plus tau, or t minus absolute value of tau, okay? And that's exactly what you get if you do it carefully. So if we do it carefully, so we have the same setting. So this goes to t, this is tau1, this is tau2, and it goes to t, and then we have here t minus tau, minus absolute value of tau, because tau is negative now. And now the integration domain is this one in here. Okay? Now the line tau equal tau1 equal tau2 is this one in here. And we are interested on the parallel, which is, oops, which is the line tau2 equal tau1 minus absolute value of tau, okay? And now you see that just as we wanted, now if you ask for what is the integration domain along the line defined by the delta function in the tau2 axis, that's from 0 to t minus tau. So then you have to do the integration in tau2 from 0 to t minus absolute value of tau, which is just plus tau, okay? Or again, you can do the integration in tau1, but now you see that the integration will go from tau to t, okay? Or absolute value of tau to t. So in both cases, the integration domain is not a whole time t, but it's less than that. It's a time t minus tau, okay? So this is the only point I wanted to make, that when you have delta functions and you have different integration domains, and the delta function depends on all the variables of your integration domain, then you have to be careful to how to select the integration domain, okay? And in particular here, if you use these two expressions, then you will get something very easy. So using this, then you get at the end an incredibly simple expression, which just looks like this. So it's just an exponential of minus lambda and the time difference tau. So then, as promised, you see that for a stationary system like this one, the two-time correlation function depends only on the absolute value of the time difference, okay? And then with this, you can evaluate in a completely trivial way the power spectrum by using the usual Fourier transform. So in particular, if we put everything together, so what we get is that the limit when t goes to infinity of the output quadratures, either the position or momentum, this takes a very simple expression, it's just a delta function plus 2 gamma, and then gamma divided lambda phi minus 1, and that's just a prefactor for the decaying exponential, okay? So the correlators in time decay exponentially with the time difference. So this is just by combining all the results that we have in here, okay? These 4 terms together, they add up to a two-time correlation function of the output that is just this expression here. Then you can do the Fourier transform of this expression. And the Fourier transform of this expression is what we define as the quadrature noise spectrum. So let me just remind you quickly that it's this expression here. Okay, if you do a Fourier transform of this two-time correlation function, you get a general expression that looks like this. We get 1, and remember that 1 was what we were getting in general from the normal order, plus, and then we have the squeezing spectrum part, so the normal order part, that in general for both quadratures, positional momentum looks like this. So finally, if I particularize this expression for the positional momentum, what I get are these two spectra. So for the position, I get 1 plus 4 sigma divided 1 minus sigma square plus omega divided by gamma square. Remember that sigma is a parameter that when it can go from 0 to 1, 0 means no down conversion, 1 means that we are exactly at the maximum down conversion that we can have in this simplified model, which is equal to the rate of decay of the cavity. And then you see in this expression that when sigma goes to 1 and omega goes to 0, we again get infinite fluctuations, okay? So for 0 frequency, we get infinite fluctuations. Just like inside the cavity, in the stationary limit, we were getting infinite fluctuations in the position quadrature. But now the interesting part comes in the momentum quadrature. So if you take the momentum quadrature, then the expression that you will find is this one. Okay? And now you see that this is very different because when sigma goes towards 1 and omega goes towards 0, what happens? That you see that the numerator and the denominator are both equal to 4. And then when you subtract to the 1, you get a 0. Huh. This is awesome. This is perfect squeezing. Okay, it's perfect squeezing. Even though inside the cavity we have only 50% of squeezing. So this is actually showing you numerically, like quantitatively, is showing you that the squeezing inside the cavity and the squeezing outside the cavity are two properties that have to be defined in different ways and actually have different quantitative values. So for a cavity that is 50% squeezed, we are getting an output field that is 100% squeezed, okay? In particular with a Lorentzian shape, you see that this is a Lorentzian shape in the frequency omega, in the noise or detection frequency, which means that you get a bandwidth in the perfect squeezing that is 2 gamma, okay? So in particular, if you plot this squeezing spectrum, so you plot V as a function of the frequency omega, you get exactly this thing in here without the signal. I mean, because we are not modulating with any signal. We will just get something like this that goes to 1 for large frequencies, but it's 0 at 0 frequency, and it has a bandwidth that is proportional or it's equal to 2 gamma, okay? So then over 2 times the decay rate, we have spectral squeezing, okay? Or the output is squeezed. So then any signal that we encode in the quadrature fluctuations of our parametric oscillator in the momentum quadrature will appear if the signal has a frequency or frequency components that are within this bandwidth. We'll have a better signal to noise ratio that if we would use just a normal cavity without down conversion. Okay, so is this clear? And then the final surprise is that actually, if you evaluate, so if you take these two relations and you evaluate what is the product of B0 of omega with B pi over 2 of omega. So I remind you that because of the uncertainty principle, this is bounded by 1, okay, from below. But in our case, this is exactly equal to 1. So if you do the multiplication of this function with this function, okay, it's not maybe immediate to see it, but if you just do it and you operate, you will get exactly equal to 1. So actually, even though the intracavity state is not in a minimum uncertainty, is not a minimum uncertainty state, the output state, so let me, is a minimum uncertainty one. Okay. So then I hope that with this example, I have been able to show you that the properties of the light outside the cavity and the properties of the light inside the cavity, even though they are related, of course, they can be very, very different. Like, and actually it's very funny. So let me just tell you a story. Like in the 80s is when this business of gravitational wave detection and measuring with Gaussian, with squeezed states and so on was kind of put forward, and when LIGO started and so on, 70s, 80s, people were thinking very hard about how to generate or how to create sources in the laboratory that create squeezed states. And then people thought, the first thing they thought is, okay, it's very easy, let's put down conversion inside a cavity. This looks like the right way to go. And then people evaluated the squeezing and they got only 50% of squeezing. And everyone was so sad for a few years. It was like, oh, come on, this source, it looked like such a good candidate, but it only gives us 50% of squeezing, which is not so much. So then people were really sad for a while, until someone, it took about 3 years or something like that, to realize that people were always talking about the intracavity squeezing. And what is used is the output squeezing. And it was not clear what was the relation between how do you define the squeezing in the output signal, so in the output field. And finally, I think it was when I was born in '83, actually, there was a paper that was showing for the first time, hey, we have been looking at this in the wrong way. The good quantity to measure is this quantity here, the output quadrature noise spectrum. And if you check this quantity, you get perfect squeezing. So this is what we can, this is a source that we can use for gravitational wave detection and for any kind of measurement that we want to do beyond the shot noise or coherent or vacuum noise limit, okay? So this was kind of this story that I have told you in just a couple of hours. It's actually something that took a few years to figure out by people in quantum optics. So it's a very interesting story. And this device, the optical parametric oscillator, it's essentially one of the most important sources of light that we have for modern applications, because it generates squeezed states of high quality, in particular, very highly squeezed states, close to 100% squeezing. And once we have squeezing, we can use it to generate entanglement, which is also very important for quantum information protocols, okay? So then this is essentially the story with which I want to finish the course. As I told you, I will not ask anything in the exam about this class of today, because I think that only 1 week before the exam is not fair that I ask for too many details about it. But it's a story that I wanted to tell you so that you understand all these relevant issues that I mentioned. And well, I think that, so it's perfect that we have 5 minutes left, and this gives me the time to just say that I know it was a kind of a challenging course in terms of material. I know there was a lot of material that we covered and a lot of, let's say, high level use of quantum mechanics, but this is exactly what I wanted to show you. I wanted to show you how quantum mechanics is used beyond the most trivial examples that you see in quantum mechanics courses. And I hope that now you feel much more familiar with quantum mechanics and that you are ready to use quantum mechanics in any context. And now that you have seen physically, let's say, timely a scenario for quantum mechanics, which is quantum optics. And since, as I told you, I know that the course is challenging, you can expect that the exam it won't be as challenging as the course. So hopefully you will all do okay. So I think that at this point I will just thank you for attending all these lectures, and I will stop recording, and then we can talk about some technical things about the exam and so on. So let me stop the recording.